In this tutorial, we will be discussing acid-base reactions. Acid-base reactions are also called neutralization reactions because the acid and base neutralize each other's properties. In the process, it's forming water. So the hydrogen and the hydroxide are coming together to produce this water. And water is a neutral compound, and that's why it's called a neutralization reaction. The net ionic equation, as long as the salt's not insoluble, is going to be H plus OH minus yields H2O. Notice it's producing water. If the salt that is produced, which is just, remember, that's just a generic word for an ionic compound. If the salt is produced, is insoluble. If it produces a solid in water, it's going to be in here too, and we're going to talk about that later on. Acids ionize in water to form H plus ions. More precisely, the hydrogen from the acid molecules is donated to the water molecule to form H3O plus, called the hydronium ion. This is the more correct term because H plus on its own does not exist. Most chemists use these, however, interchangeably. Acids can be broken down into not only single hydrogen atoms given off, like HCl or HNO3, but it could also be polyprotic, poly meaning many, and protic referring to the H plus. If we look at the chemical formula for hydrogen, it has one proton and a mass number of 1, meaning it has one proton and 0 neutrons. That means that once that electron leaves, that proton is the only thing left, which is why it's considered a proton, and H plus is being used interchangeably as well. Acids which contain more than one ionizable proton release them subsequently. So in other words, with H3PO4, it's going to release one at a time. So it's going to go to H2PO4 first, and then it's going to release the next one, HPO4 2 minus, and it's going to keep going. The first one's the easiest to remove, and then every time you remove another hydrogen, it gets more and more difficult. Diprotic is simply one that has 2 hydrogens to give off. And then triprotic would be like H3PO4, where it has 3. Bases dissociate in water to form hydroxide ions. So we have the hydrogen from the acid and the OH from the base, and they come together to make the water. Bases like NH3 here, that does not have an OH group, produce OH by taking the hydrogen from a water molecule. So this hydrogen goes over to NH3, which leaves us with OH minus left, hydroxide left. In the reaction of an acid with a base, the H plus from the acid combines with the OH from the base to make water. The cation from the base combines with the anion from the acid to make salt. That's an ionic compound. We're going to do some examples of these as we go along. So just to give you an overview, here's a few common acids. We have nitric acid, which is used for explosives and fertilizers. Hydrochloric acid is another very strong. It's used for food prep, and it's actually in your stomach for stomach acid. Acetic acid is actually vinegar, and that's considered a weak acid. Some common bases, sodium hydroxide, potassium hydroxide, and calcium hydroxide, all have the hydroxide in common. Sodium and potassium are both alkali metals, whereas calcium is an alkaline earth. Notice that those all three are considered strong, although there are some OH groups that do form weak acids. Like milk of magnesia is magnesium hydroxide, and it's an antacid, and it's a weak acid. Or weak base, I'm sorry, weak base. Alright, so HCl and NaOH come together to form NaCl and H2O. You can do this like you were doing a double replacement reaction from before. The outside ions come together and the inside ions come together. So the H is now with the OH. So this is the same thing as going like this, and you just rearrange the chemical formula to form the H2O. And then the Na is with the Cl. So plus 1, minus 1, crisscross it to get NaCl. So originally, they both go in aqueous solutions. So HCl is floating around with water. Notice when the chlorine's by itself, but the hydrogen is connected to the water molecule. It's not floating by itself. NaOH, however, the sodium is floating by itself and the OH group is floating by itself. Then when they come together, water is formed. And that NaCl is now aqueous, and they're both floating around in the water. So they were here at the beginning, and now they're here at the end with the water molecules around it. So let's take a second to practice this. Write the molecular ionic and net ionic equation for each of the reaction equation, aqueous of nitric acid and calcium hydroxide. So, the inside ions come together and the outside ions come together. So H goes with OH, and that produces H2O, and we know that that's a liquid. So that's one of the products. The other product is going to be Ca2 plus with NO3 minus. Crisscross those, and it becomes CaNO3 2. Now we need to see if this one's soluble or not. So we're going to check our solubility chart. And we will see that NO3 is soluble with no exceptions. So our products are H2O as a liquid and CaNO3 2 as an aqueous. We can now balance it. We have 2 nitrates over here, so we're going to multiply this by 2. We have 1 calcium, 1 calcium. We now have a total of 2 hydrogens here and 2 hydrogens here, which makes 4, which is why I want to multiply that by 2. Alright, now that we have a balanced chemical equation, a molecular equation, let's do the complete and net ionic equations. Whenever you see AQ, you're going to break it up into the positive and the negative. So we have H plus aqueous, and there's going to be 2 of them. We have NO3 minus aqueous, and there's going to be 2 of those. We have the aqueous here, so we're going to break those up. Ca2 plus aqueous, I only have 1 of them, and OH minus aqueous, and I have 2 of these. I have aqueous here again. Break those up. Ca2 plus aqueous, NO3 minus aqueous, and I have 2 of them, and 2 H2O liquid. That's not aqueous, so I don't break it up. Now I want to write the net ionic. Remember, there's 2 different ways you can do it. You can look at what is formed, 2 H2O, and look at the ions on the other side, 2 OH minus and 2 H plus aqueous. Or you can go through and figure out which ones are the spectator ions and just remove those from the equation. Let's try another one. We're doing HCl and BaOH this time. Inside comes together, outside comes together. So the outside's easy. HOH gives us H2O as a liquid. The next one is Ba. That's a 2 plus charge. Cl is a minus. These charges, once again, are coming off the periodic table by what row they're in. Crisscross it, it becomes BaCl2. Now we have to look at the solubility chart. And we see that Cl is soluble except for these, and barium is not one of the exceptions. So therefore, this is going to be aqueous. So BaCl2 is aqueous, and so water is a liquid. Now let's take a second to balance it. We have 2 chlorines, so we're going to put a 2 in front. We have 1 barium and 1 barium. We have 1 oxygen on the right and 2 on the left, so I'm going to multiply that by 2. So that gives us 4 hydrogens. So we have 2 hydrogens here and 2 more here. Alright, now that we have a balanced molecular equation, let's make it a complete and net ionic equation. We have aqueous, so we're going to break those up. So H plus aqueous, Cl minus aqueous. We have 2 of them. We have aqueous here, so we're going to break those up. Ba2 plus aqueous, we only have 1 of those. OH minus aqueous, we have 2 of them. Our next thing is water as a liquid, so we're not going to break that up. And then we have aqueous barium. And we have chlorine aqueous. And we have 2 of those. Now, we have water, that's the only thing that's not aqueous, so 2H2O. And the ions that make that up are 2H plus aqueous and 2OH minus aqueous. For our last example, we're going to take sulfuric acid and mix it with strontium hydroxide. Insides and outsides. The outsides are easy because it's going to form water. HOH, H2O, and we know that's a liquid. Now let's look at the strontium hydroxide. Strontium is a 2 plus, sulfate is a 2 minus, crisscross. They cancel each other out, so it's going to be SrSO4. Now let's look at our solubility chart. SO4s are usually soluble. However, strontium is an exception that makes it insoluble. So that's actually going to be a solid. So it's going to be H2O liquid and SrSO4 solid. Okay, balancing it. We have 1 strontium, 1 strontium, 1 sulfate, 1 sulfate, 1 oxygen. We actually have 2 oxygens. And that balances out our hydrogens. Because there's 2 from the sulfate, from the sulfuric acid, and 2 from the strontium hydroxide. Alright, so let's do the complete and net ionic equation here. Whenever you see aqueous, we're going to break it down. So, H plus aqueous, we have 2 of them. Sulfate, aqueous, we have 1 of those. Strontium is a 2 plus, and it's aqueous, and we only have 1. And hydroxide is a -1 aqueous, and we have 2 of these. And that's going to yield 2H2O. It's a liquid, so I don't want to break it up. And this time, strontium sulfate is actually a solid, so we're not going to break up that either. And as a result, because there are no spectator ions, the complete ionic equation is the same as the net ionic equation. Alright, that gives you an overview of acid-base reactions.